that she executed successfully. And I'm going to show you what's Light. Okay, so now what am I going to do, Pedro? Edit the input. Okay, this is a description of the project. These are headers that can be identified by someone searching the databases of calculations that have been done. So you include the chemical formula, the type of project that has been executed, a structure, material, and exchange correlation, and so on. And some information about the number of processors that was used per core, and some other parallelization parameters here. So now I don't want to go back, right? Cancel. I don't want to do this anymore. So edit input. This is how the input is prepared in VLab. This is the interface. We are going to do optimization in a certain number of pressures, and these are the pressures that we want to optimize the structure. This is crystal information about the crystal structure. Oops, it's the next step, right?
There's a scroll down. Yeah, you scroll.
It doesn't go anymore, Pedro.
No. There's a lower back there. There's a scroll. Just go to the no.
Come on.
Right here.
I have to go to edit input. Next, right. Where's next?
Yep.
Okay, oh, see. So here is more information about the project. Yeah. So this is the next page, and it has information about how many MD steps you want to execute, an approximate equation of state that facilitates a lot and speeds up a lot the structure optimization at each pressure. So these are the next cell parameters and the strains that you want to calculate, and some information about the electronic structure itself. Is it a metal? It's not. How many what's the energy cutoff that you want to use? Information about K-point sampling, and so on. Next is, yeah. So all the information about the project has been input. That was the input, and the project runs successfully already, and that's how, after you submit, that's how you would monitor the project. So here are monitor the execution. Here you have several stages. The first stage was the approximate equation of state. And the second stage is the refinement of the equation of state. 8 tasks were executed. And the third stage, 9 strains versus 8 volumes. We have 72 tasks that execute. Each one of them used 32 cores. So when the first task, for example, is running, and you want to monitor if the calculation is proceeding properly, so you click details, and you can view the output. If the output is very large, and usually we download the output, and that's done quickly, but I'm not going to do here now. And you can inspect the output while it's being produced. Okay, the project ran successfully. And after the second, back to monitor, okay. After the second stage was completed, you can already check what was the equation of state. Where is the? Yeah, okay. You can check the equation of state, the result from an accurate calculation. You can view fit, which is, in this case, it's the Vinay equation of state that was used to fit, but it doesn't have necessarily to be that. It's transferring data. Okay. Now, so here the third stage was finished correctly as well. It was completed successfully, so we can go back and look at the elastic constants that resulted. This was an orthorhombic system. So we can look at those numbers. It's calculating the elastic constants from the outputs, the total energies and the stresses in the output. Waiting. It's running, but it's running in our server, small server in CMS. And the results can be plotted as well. And you can interact with the plots. OK, so this is a typical table. You have pressures, all the 9 elastic constants. The 9, they are not here, Pedro. I don't think we calculated for an orthorhombic system. No, yeah, they are here, yeah. So let's inspect them. So I want to plot maybe just 1, 2, and 3 in one plot, or I can plot all of them together. I can already choose as many plots as I want. Yep. Right. OK, let's look at the first plot. Oh, no. This is, yeah. So here are the 9 elastic constants plotted. And you can interact with the plot. You have the controllers, above, and you can change the pressure or so on. Or we generate 2 plots at once. This is just for the first 3 elastic constants. So you can go online and see a movie that we have there that shows you a project that consists the thermal equation of state of MGO. It's a small project, and you can see it running in real time. Of course, after it runs, the thermal properties can also be calculated as we do here. Here is a collection of results that we make available online. These are results that we published. But behind this, what there is a vibrational density of states versus volume, and the program, the thermodynamics code that you can use to run yourself with the vibrational density of states we produced. You can experience by yourself what the thermodynamics properties depend on. Every calculation, you're going to have a grading temperature, you're going to have a grading pressure, and equations of state to fit. How these results depend on these choices. You can go and do it yourself. If you don't know what to choose, you can fill the default values that are used in our publications, and then you can play with those. Here, you can also choose if you're going to plot as a function of temperature for several pressures, or vice versa. And you can choose the pressures that you're going to plot. So it's an interactive way to reproduce our results. We believe these results are pretty useful, all the thermodynamics properties of these minerals. So here we are recalculating. So we are generating all these properties here. And you can download the files. You can view the data. Let me show you what the data is. You have these tables. Here's the thermal expansion coefficient as a function of pressure, of temperature for several pressures. You can see all the other thermodynamics properties. That's it's taking time to transfer here, that's all. So this is, all these tables can be downloaded. Or you can go and view the plots, interact with the plots, and so on. So these are resources, some of the resources that we have available. OK, I want to plot thermal expansion coefficient. OK, change the ranges, interact with the plot through these controllers here. So this is also possible. So we have also other resources that we made available there. For example, I think this resource would be useful for someone who's trying to learn how to do calculations of thermodynamics properties using the quasi-harmonic approximation. The code is available in another site if you want to download, read by yourself, and read and use the input that is there also and play with it. You can do that as well. Other resources that we made available here are some highly accurate equations of state that we use by combining experimental data and calculated data for MGO and for platinum. If someone is interested in using this as a pressure scale, this is how you would use intertemperature and lattice parameters of MGO for a certain number of data points you have, and you just get the pressure. The same can be done for platinum. And finally, just last thing, the database. These are projects or results that have been produced within VLab, and these are examples that you can use, can check to learn how to submit your own jobs later. But for example, you can. This works like the Web of Science. I'm going to search if anything has been done in Wadsley, lowercase, okay, in Wadsleyite. So, okay, there are several projects on Wadsleyite, and they were executed by Mary Bell. One is, both are about elastic constants. One has iron, the other doesn't have. This was done with local density approximation, and so this is the type of the way I saw her project. Any collaborator would be able to see as well. So this is a system that was designed for collaboration. Of course, we are making her unpublished results available here just to show to you, but in principle, not everybody should be able to see this, only the collaborators. There are several levels of access that we can give to the world, the group, to the or to nobody. So I believe this could be instructive for people learning how to do these types of calculation. And of course, the system today run only the quantum espresso, but it's the executable is not an issue. Could run other systems as well. So this is all that I want to show today. And I think I spoke too much already. So thank you.